get the recording started so that we'll have this for the future. And first of all, let me just ask everybody to, if you want to let me know of any problems you're having, or maybe some challenges that you overcame getting set up.
This is Jonathan. I'll just start by saying I actually have no issues. I'm just monitoring to see what else I can learn. I've got the different operating systems installed. I've got GNU Radio running on Raspberry Pi as well, and I've gone through the exercises and think I understand them. So thank you for that.
That's great, Jonathan. Do you have prior experience, or are you an EE?
I'm definitely not an EE, and in fact, that's my big weakness. I am a software engineer, and I've used GNU Radio as software, and I'm familiar with Linux, so that part doesn't pose a challenge. What does pose a challenge for me is my lack of foundation in the RF world. So that's where this is really benefiting me.
All right, very good. That's um, I guess I never thought about somebody coming from that background, but those are great combinations to have. And then, what we can maybe help to impart to you, that'll be good. I'd like to see if we're successful in that regard as we go along here. Anyone else or the next person? Okay, I'm not hearing anybody. So we'll go ahead and jump in here. And I in the spirit of overlapping, I kind of want to go back and review some basic stuff and then take us back into IQ or quadratic sampling, and then kind of end up today with just a transmitter concept, because I think as I was going through this, it seemed to me that the transmit side was a little easier or intuitive to understand, the trig identity and the reason why we find a convenience in adding together the I and the Q components. You'll see what I mean, I hope, when we get to that point there. But first of all, let's just start with somebody asked me, well, why is there an I and Q? Why is something 90 degrees out of phase from something else? And we find that there is a orthogonality achieved through two signals, two sinusoids that are 90 degrees out of phase. And with orthogonal functions, we can do a lot, and we will touch on one of those today, but there'll be a whole lot more as we go on. I think it's real important to understand a little bit of the math and a lot about the complex plane if you can take it, because those principles in theory carry on in everything that we do in SDR and in DSP. I and Q basically are represented by a complex number, which is just two numbers. One will be a real component, one will be an imaginary component. We've talked about that in the past sessions. We'll talk about it some more today and review. And then one of the main things is the SDR architecture and radios, they spit out two numbers on receive. They actually just stream these complex values that represent the sample that has been taken according to what we have established as a sample rate. So in GNU Radio, we will have to indicate a sample rate that will get downloaded to the radio at initialization, and as well as some other variables or parameters such as the center frequency. And then we will begin to enjoy just a stream of complex numbers coming into the flow graph in GNU Radio or into whatever SDR software you're using. And those pairs of numbers is what it's all about. And then on the output for the transmitter side, the radio expects the same. So it expects a series of complex numbers to be delivered to it, which it will then interpret into a single sinusoidal wave that will be modulated and transmitted over the air. So I'll start by just going back to something we showed before. let me see if I can minimize some things and expand some things. Okay, so we talked about real signals that a real sinusoid that leads a imaginary. And so this was the graph that we used. And let me get something that writes good on the board here. I think this one's all right. And so we'll draw a complex plane here. Well, there. I guess I didn't store that one nose down, did I? Terrible. And so let's just say that these values are 1 and -1 and -1 here on what otherwise could be a Cartesian plane. And this is our I axis, this is our Q axis. And for a positive signal, I've got this pair of sinusoids, which was a picture taken out of GNU radio with a stem plot turned on. So I've got it numbered with crest and zero crossings and crest and zero crossings. And so we could put numbers by these, and we did before. So let's just go through that again. And I'll start with the number 1, which is a peak on the real signal at a value of 1 and a 0 on the imaginary signal, which is right at that junction where my cursor is pointing. And so for the Q to be 0 and the real to be 1, we're talking about this point right here. And then there is a smooth curve that sees a descending value on the real signal and a rising value on the imaginary signal. And so when we reach point 2, there will be we've now come to 0 on the I-axis, and we've reached a positive 1 on the Q-axis. So that's that point there. So all these points in between are starting a counterclockwise circle, which is what we've come to know as a positive frequency. So this is the second point. This is the first point. Now, I'll continue with this, and then we'll come back and put the complex numbers in. But 3 would be a -1 on the real. I'm sorry, do I have that right? 3 would be -1 on the real axis and a 0 on the Q. So Q has come down to 0, and now real is at this point. And so we're going to come around here, and that's number 3 point. And you might guess that the next one is going to be a real value of 0. So real has come back to 0. And imaginary is now crested at the lowest point, which is -1. So that's number 4. We clearly have counterclockwise circle or counterclockwise rotation. Now, to number these points, we know that this one here was a positive 1. So the first number is a 1, and the second number is a 0, imaginary. And then this one here is going to be the first number 0, because the real number comes first. And then it's a positive 1, imaginary. And then this number here is going to be -1, because the real number comes first, and we're -1 on that axis, and a 0, imaginary. And finally, at this point, we've come 270 degrees and or radians, and we are now at 0 again for the real number and -1 imaginary. Now, what really happened here, I didn't point this out before, but really on the imaginary axis, I'm sorry, the I-axis, the real axis, this value is just moving back and forth. See the positive 1, it's not achieving some other, it's achieving these intermediate values here, but it's really just rotating back and forth here. Whereas the Q is doing just the opposite, and it's moving up and down on the positive and on the negative imaginary axis. I think that's important to to point that out. I had not done that before. Now, if we bring in the other picture that I made, this is, I guess that one's gonna need to be clicked and gotten rid of. Maybe I can set this one here. Okay. How about that? So this is just the opposite case where imaginary is leading real. And so I, kept these colors here like this from the stem plot, and you would just find that it's starting up here. So it's starting up here. And where is the real? The real's lagging, starting down here. And what are those? 90 degrees. So it all lines up, and it's making sense to what it's supposed to make sense to in terms of the theory and radio. Now I'll clear this off and make a little room to draw some more stuff on here. And if I can get it erased. Any questions on this so far? Doesn't take long for that to almost get permanent. Either that or I'm getting weaker and weaker as I get older and older. I think there's a little bit of both there. All right, that's probably good enough. Let's just go back before we jump any further into how we get on these, how we get on that plane, and how we have a signal to work with in the digital sense. And let's go back into sampling, and we'll go just through some basic sampling theory, and then we'll go into quadrature. And so we'll start with, we've got, I'm going to give up on that one and use this one. We'll start with time. 1, 2, 3, 4, 5, 6. I think 7 works best. And then we're going to have a signal that's going to be coming to us through time. And then we got to take samples. So if we take these samples at the same frequency that we've got in the signal, that would put the samples, let's say the first one's there, the second one would be there, third one would be there, fourth one would be there. Now, the problem with that is if you're going to recover the signal from those samples, that's not looking too good, because this is what you'll reconstruct, which is not the original signal. So this is highly undersampled. I don't think anybody would have any problem understanding that. Now let's raise the sample rate to 1.5 times and look at that one. And you can definitely simulate this in your GNU radio and see the problem, because all kinds of bad stuff happens. Okay. Once again, we got time, got a different color, but 1, 2, 3, 4, 5, 6, 7 divisions of time. I got a signal. Which conveniently goes through the time marks. And then a sample of 1.5 would look like this. It's going to be about here, right? It's going to be about here. It's going to be about here. It's going to be about here. It's going to be about here, about here. So it tries to do a little bit better, but the problem with this is you could actually have a recovery that would look like this. I don't know how I'm going to get back down to that one, but anyway, you can already see that it's about twice the frequency, and that's what happens when you're still undersampled there. So we know from our experience so far that you have to sample at least 2 times the frequency, or you can say 2 times the bandwidth where there is a discrete signal in that bandwidth. So let's go back one more time and do it right. Frequency. And sampling at 2 times, if we're starting there, the next one will be there, 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 and there. So there's no way you will get any other signal to match those sample spots except the one in blue until you go to a much higher frequency. And when you go to a much higher frequency, then there's a match, which is a different kind of problem because once again, you haven't got your sample rate high enough in that scenario. So this is our basic sampling. Any questions on this? Okay. It's what we've gone over before. And you can illustrate this in a couple of ways. I have written some Python that does it. And you can kind of get it plotted in, or you can definitely get it plotted in GNU Radio by just changing the time domain graph to output dots. And then you'll see the samples that have been taken. You'll have to slow things down to be able to see anything other than a blur. Okay. So now we'll state the obvious here one more time for the Nyquist rate, but basically a sample rate has to be greater than 2 times bandwidth. And don't let that bandwidth confuse you. It's really 2 times the highest discrete frequency in the bandwidth. Our SDR radios, like your Pluto and your RTL SDR, they are designed to filter frequencies just above the 2x sample rate before it's sampled. So in other words, it's looking at the frequency here and it sees it drop off and there's the noise level. It sees this and it starts off by filtering that before it tries to sample. This is, I've got you in the frequency domain, but this is what a spectrum analyzer would look like. And it will chop as much of this off high and low with a low pass filter before it samples to what's remaining. So it's trying to help us. And of course, that takes a physical filter in the radio. Okay, now talking about quadrature, we know that this is 2 waves 90 degrees out of phase, and they give us the ability to use the orthogonal functions. And I'm going to start off this discussion with setting 2 variables for us that we should try to absorb and understand and refer to in the future. And so I'm going to say let I, which is our in-phase component, which is the horizontal axis in the complex plane, equal cos or cosine of 2 pi times some frequency times some time. And then let Q equal sine of 2 pi, some frequency, some time. And these variables we'll try to stick to, or these designators we'll try to stick to represent the trig, and labels are our coordinates and the examples. So I'm going to erase this. We'll go back over the standard quadrature signal that's set at a value of both of the cosine and the sine is set at 1. The illustration we've used before and that we've shown from GNU Radio. And I could pull it up, but why don't we just draw it out here? Again, and we'll say this is 0.5. This is minus 0.5. This is 0. This is minus 1. This is plus 1. I'd really like some different colors. I'm going to have to practice with these new markers. They don't seem to have been charged good. So the sine, here we go again, will look something like that. And this is what? This is Q. And the cosine will be 90 degrees behind. And so this is the I. There. I didn't get these down to 1, which they should be, but you get the idea. We've been over this, and GNU Radio does a lot better job than I do. So we'll call the I the in phase, the Q the quadrature component that is 90 degrees out of phase, reading from my notes. And then I mentioned that we can use the transmitter point of view to take this concept a little bit further into some of the math, because it should make sense when we demonstrate how varying the amplitude of these two components is. All you have to do to change the single output sinusoid that's going to come out of the radio itself. Now, all that stuff is done with analog components for many, many years, and some of you and I have been around a long time. I was trying to tell my wife the other day, because I just built a greenhouse out back for her. It came in 5 boxes weighing 500 pounds total. And I just got it done and got the silicone sealant on 24 hours before that rain hit yesterday. And I told her, I said, there used to be a company named Heathkit. And when I was 13 years old, I was saving my money. And I finally had enough money after a long, long time of saving. I had enough money to buy an SB401 single sideband transmitter to replace my DX100 that I'd had since my novice days. And that kit came in a big box. Everything was in a plastic bag, and your panels had tissue paper on them, and there was a chassis that had the holes punched. And some of you remember those days, and the tubes were in their cartons, and we made it work. And it was step by step by step. And her greenhouse had 90 pages and something like 105 steps on it. And it was dimensionally accurate. It went together well. I was very happy that there were no missing parts. In fact, there were some extras when it came to the nuts and the bolts. And so I was trying to make her understand about Heathkit, and she would just give me one of those looks like, I don't know what planet you came from. But now you just call HRO and buy an ICOM. All right, so let's go back to this task of transmitting the signal. And we know that that requires a single sinusoidal that is modulated to launch into the ether. And so how does the I and the Q figure into that, and how does it end up being a single signal? Well, that's where there's a trig identity naturally. And I'm going to write it up here, but we're not going to tear into this one real bad on this meeting, but I do want to take us further on it. So it's if A is the cosine of X plus B is the cosine of sine X, then that equals the amplitude of cosine X minus the phase. That's a phase, not a zero. So this could be written for a transmit signal. You could have X to the T or XT equal to I. Now we're back to I cosine 2 pi ft plus, stress that, Q sine 2 pi some F some T. And that's all you have to do. That'll get you a transmit signal. Now, you can certainly multiply, quadrature sample signals, and the math is completely different in terms of complexity, and we really need to have exponents to do that. But adding and subtracting is really all you have to do for simple forms of modulation to get a transmit signal. And so that's kind of where I want to start, is to carry this on through to the simplest of transmitters, not CW, but at least AM, and demonstrate, how this math actually turns into a signal. Okay, I hate to kind of erase this one, but I'm going to. I can show it to you in code anyway. Maybe I won't have to come back here to the board, but I've got it semi-erased anyway. All right, so let's pull up the program I wrote, which you should be seeing it now. And there is a lot of effort goes on here to try to get the GUI part to look nice and pretty. But basically, all it's doing down here is displaying, there's going to be a slider where you can change the value of I and change the value of Q. And then there's a resultant curve, and that's what's important here. And this is just an addition of wrapped up in here is the 2 pi, but x cosine x plus x sine x. And so that's the result. And if we run this, if I clicked it twice, it might have one window hidden. I don't see it. Let's try that again. All right, so let's go to a place that we know, and that'll be like I and Q equal to 1. Let's see, I think I can use arrow keys here. I was trying this earlier, and it would get awfully close to 1. Yeah, got to 1. And then if I set Q to 1 also, this is a place that we just came. So we can see that the cosine starts at 1, which it should, while the sine, the red graph, starts at 0, which it should. So you're seeing cosine and sine go through its first period here. Now, the addition of the two is resulting in the green dotted line. So that's the sum of the two. This is what happens when we add two 90-degree sinusoids. They produce a third that is this amplitude, as the green dotted line shows, and phase that's shown. So if we vary either one of these components, we will change the resulting green line, which is our output sinusoid that's going to go to the antenna. And all we're having to do here is vary the amplitude of I and Q, not the phase. That's really the utility here, or the takeaway. So if I vary the real component, you can see that when I get to 0, the output is very close to a single sine wave. Much the same happens with the Q component. Adding, now adding a negative value. So again, the utility here is that in GNU Radio and all the blocks and everything that we have to do to simply add this cosine and sine values together, we can impact both the amplitude of the resulting from the add and the phase of the resultant from the add. And that is a whole lot easier, not only for us and our brains, but also for the computer to do adds and amplitude changes rather than have to do phase changes as well as amplitude changes. I'll put this Python code up on the NTMS website so that if you have a Python editor and you want to play with it, you can download it and put it in your editor. This, before we leave, this might be also interesting to set this down around 75.75, where instead of starting off with so much amplitude, you're kind of starting with lower, and I found it a little easier to see the result here as it's moving the green line one direction or another. I think you can probably see how we could get FM and AM from here. And of course, ASK by just having a hard stop, hard on and off stop. All right, that's really all I have for today. I want to pick up again at this point and go a little deeper into the trig identity and why we don't want to work with it if we can help it, and stick within the GNU radio blocks unless we have to build something particular. We can use Python like you see here. In fact, let's look at one of those examples. We can see, have we got, no, I don't have GNU radio open. Let me open it. Okay. Yeah, if you take this, I'm having to move windows around that you can't see. If you go into, I think it's view and check this generated code preview. That will enable you to see the code that's generated. So if we look at this Pluto block, for instance, and look at the generated code, here's the data that it actually sends out the port. And it's what you would expect. It's going to set the center frequency. It's going to send out the sample rate. It's going to send out AGC mode. It's going to set a gain value. I didn't know there was a choice whether you could get quadrature or not, but it is setting that true. And then it's setting the parameter to auto for the filter parameter. And you can go through various blocks like that and look at the generated code. So you could build one of these blocks. We probably should do a session on that. And it would be your private block, and you can make the code what you want it to be. There's filter won't be too interesting, I don't think, but so that's really all I have today. Are there any questions or discussion? Anyone want to talk about some of this?
Nothing for me, but thank you very much for that background again. That still helps. Really appreciate it.
I have a question for Jonathan on, you set this up on a Raspberry Pi
I did.
and you're running Dragon OS or?
No, I'm running Raspberry Pi OS, so just using what was available in the repos from Raspberry Pi Foundation. So nothing super special.
Okay. I'm thinking that might be faster than the old laptop that I've got this Dragon OS on.
Yeah. I mean, it truly can be as simple as just doing, the apt get install GNU Dash Radio, I think is what it is. I'd have to think. Now, that may or may not install all of the components that you'll need to drive something like the Pluto, but those are available in the same repositories.
Yeah, I've got to find my Pluto. I have one somewhere.
Right.
So Chuck, tell us your story. And you
Oh,
ended up with Dragon OS, right?
yeah, I tried to load stuff on my old, I say old, on my formerly work laptop, um, which about 4 years ago, 5 years ago, was a high-end laptop with, and it didn't like it. Getting the display right and everything didn't work. So I ended up going 2 generations back and that got Dragon OS to load on a laptop so old that the only extra video display is VGA on it. Um, and I have probably too many high resolution displays that I got because I had a customer that wanted me to do some PC board layout, and I really don't do that. Um, I give the other people some background. I'm a old line RF engineer, and I've actually been doing RF front ends for software defined radios for about the past 5 years. And looking at it and sampling in the first Nyquist zone, which is what Jim's showing, I think the Pluto samples in some of the higher Nyquist zones, and so does the RTL dongle to get it, which is a way to get to make do with a slower A to D converter. And today, that's for the commercial boys, that's almost moot. Um, I think both Intel and AMD have got 64 gigasample A to Ds and DACs. So my things of making down converters and stuff for SDRs, that's going away.
I think we should still probably cover down convert and up convert because of the kind of SDRs that people are going to have here. The
Uh,
Pluto, the Hack RF.
People can't afford those, the kind I
Right,
just talked about.
right, right. So the idea, you guide me along here. I'll try to draw that out here, but basically, we have an antenna here, and we've got a stage here that needs to do a little bit of a down convert in order to get it away from like 100 megahertz and take it down to 10 kilohertz, a very samplable frequency, right? But you're dealing with something that comes right in here and it can handle the 100 megahertz straight up.
Well, the Flex Radio does that today. They've got a 243 megahertz sampling, so they
So
could do
it'll
100
go up
megs.
to 100 something megahertz. But
Oh, it'll
is it tied to the antenna, basically?
no, actually they have filtering to limit it, but um, their converter could do that. Um, and it, I would go so far as to say you can get into the higher Nyquist zones, and that does work. Um, but I think as sampling different. I think of it as mixing. Um, and so you get a image as well, and the second Nyquist zone is effectively the image of the sampling.
That's a physical mixer, right?
That's a physical mixer, but sampling is the same thing as this physical. Sampling is a physical mixer.
Yeah. Okay. No argument there. A resampler might be in software. Right. So we're still in the world of, a few $100s for a radio. And I know that those real high end A to D converters are very expensive, but they uh, achieve a more efficient, you know, that's direct conversion. The way I look at it, I don't know what a professional calls that, but that's not, there's no IF and there's no zero IF. It's just direct conversion.
I might think of it as a phasing rig, predating the filters for single sideband radios.
Interesting. Well, we've got you, the hardware front end expert. We've got Jonathan, who's software based, capable of understanding the in guts of GNU radio. Um, Richard, I'm sure you're bringing something to the table. He's on mute. Well, okay, I guess that's enough for today. I'm ready to crack open a beer and go look at her greenhouse again and see if I can talk her into pouring some of the gravel on the ground. With that rain, you could tell there was a little bit of damp ground from the slight slope in where it's located because it's right on the ground. It's on concrete blocks, but it's not on a concrete foundation. So I got to get her to help get some gravel down so that when she's walking in there, she won't be walking right on wet ground. So if there's no other questions, I'll give you one last chance. We'll wrap it up here. And I'll put the recording up on the website.
Very good. Well, thank you again. I appreciate it.
Thanks for your attendance, Jonathan. Chuck, always good to talk with you. And Richard, we will catch you later.
Yeah, I apologize for missing some of the other ones. I have too many, being retired, I have too many things going on.
Well, I can't wait to have that problem. It's not much longer for me, about another year.
Good luck.
Yeah. See y'all later. Bye-bye.